Hello, my darlings. Okay, today we're going to look at global and local extrema, and we're going to look at increasing and decreasing. So, what's the difference between a global or an absolute extrema versus a local or a relative extrema? Well, a global or absolute maximum means that f of c is the absolute biggest value of f of x, and that's only true if f of c is greater than or equal to all values of f of x for all the numbers of x in the domain of f. It is the absolute highest point anywhere on the graph. Now, a local relative maximum means that f of c is a relative maximum if and only if f of c is greater than f of x for all numbers of x in an interval around c. That means if we have here c, over here we go a little bit this way and a little bit this way, and c is going to be the highest point in that small local area. These are usually turning points. Okay, the graph is going to go up, get to its local maximum, turn around and come back down. Okay, now global or absolute minimums are very similar. If you have a global or absolute minimum, it is the absolute lowest the graph goes anywhere on the graph over the domain. Whereas a local or relative minimum, the graph goes down to a low point, turns around and comes back. But the graph might go lower someplace else. So here we have two local minimums. There's one here and there's one here. Those are both two local minimums. Okay? So one of the things we need is to know what a critical point is. A critical point of f of x is a point where the derivative of f of x is 0, or where the derivative of f of x does not exist. And critical points are going to help us determine when a function has a relative max or a min. Critical points will help us find where max and minimums may occur. A little more work is going to have to happen before we know for sure. Let's just take a look at a graph. So here's a graph. Now the absolute maximum, the absolute highest our graph ever gets, is right here at D. The absolute lowest our graph gets is right here at A. Now a relative maximum would be this turning point at B, where the graph goes up, turns around, and comes back down. That's a relative maximum. And a relative minimum would happen right here at E. The graph goes down, turns around, and comes back up. Okay? So something to keep in mind here, that all of the relative maximums and minimums occur where the derivative is 0 or does not exist. They do not happen at the endpoints. So notice E is neither a relative max nor a relative min. At the endpoints, you can only have an absolute max or an absolute min. No relative maxes and mins, because relative maxes and mins are turning points, and you're not turning at an endpoint. It's stopping. Let's look at another one. Okay, so on this graph, our absolute highest the graph ever gets is when we're at the x value c. The absolute lowest this graph ever gets is right here at b. Now, a relative maximum, do we have a point where the graph goes up, turns around, and comes back down? The only time we have that is at c. But we already called c our absolute maximum, so we have no relative maximums. Okay? Now, a relative minimum, where the graph comes down, turns around, and goes back up, would be right here at D. Now, yes, B is also a turning point, but we call that one our absolute minimum. Now, notice in this graph, the minimums occur at points where the derivative does not exist because those were cusps and there are no derivatives at that point. Now, important to mention while we're here is that not all functions have a maximum or a minimum value. Notice this graph is rising forever and falling forever. There's no maxes and mins. There's also, because of these asymptotes, no turning points. There are no maxes and mins. Now, the next one, this looks linear, right? So it should have a max and a min, except for the fact that it ends on open circles. It has no max and no min. All right, just a little bit about the extreme value theorem again. Hopefully you remember the extreme value theorem. So there are two cases. The extreme value theorem for the maximum case says that if f is continuous on the closed interval, then there exists a number c in that closed interval such that f of c is greater than or equal to f of x for all numbers x in the closed interval. The number f of c is called the absolute maximum value of f on the closed interval. Remember, the extreme value theorem says, and these first two theorems are the very formal ways to say this, okay? This is the rigorous calculus. The extreme value theorem, the minimum case, if f is continuous on the closed interval from a to b, then there exists a number c in the closed interval such that f of c is smaller than f of x for all numbers in that closed interval. The number f of c is called the absolute minimum value. Notice f of c is a y value, that's why it's the minimum value of f in that closed interval. Remember, we talked about this before. A function that is continuous on a closed interval must have an absolute maximum and an absolute minimum on that interval. That is the extreme value theorem that we talked about back in the first unit. The key for the extreme value theorem, you are continuous on a closed interval. A graph has to have a max and a min. There's no two ways about it. Just a little word about the three value theorems, okay? What do the intermediate value theorem, the mean value theorem, and the extreme value theorem have in common? All three guarantee the existence of a function input, an x value, that has a certain property. Any AP problem that asks about the existence of a function input with a certain property, so they're looking for an x value for some c, some x value c, okay, with a certain property is probably asking you to apply one of these three theorems and expect to be asked one of these questions, okay, to use the intermediate value theorem, that if you know the function values, that there's two function values on a continuous interval, it has to take on every function value in between. The mean value theorem, if it's continuous on the closed, differentiable on the open, then f prime of c has to equal the average rate of change on that interval, okay? And the extreme value theorem, if you're in continuous on the closed interval, you have to have an absolute max and you have to have an absolute minimum. One of those three theorems, okay? Now, let's just talk a little bit about increasing and decreasing functions. When a function is increasing, bigger inputs mean bigger outputs, right? The bigger x gets, the bigger y gets. When a function is decreasing, bigger inputs mean smaller outputs. So as the x's are getting bigger, the y values are getting smaller. Now, a positive derivative tells us that the rate of change. So now I'm changing it. When a function is increasing, bigger inputs mean bigger outputs. A function is decreasing, bigger inputs mean smaller outputs. Now, if we look at a positive derivative, that tells us that the rate of change of the function is positive, which means the function has a positive slope. If you have a positive slope, that means an increasing function value, okay? If the negative derivative, that tells us the rate of change of function is negative. If the rate of change is negative, that means the function has negative slope, so it's going down. That means decreasing function values. So it's very important to note here, when you are justifying increasing or decreasing behavior of a function, we say that f of x is increasing on a closed interval because f prime of x is greater than or equal to 0 there. Okay, don't forget the or equal to. f of x is decreasing on the closed interval a to b because f prime of x is less than or equal to. So it's not just when the derivative is positive or negative, because remember, our definition of increasing said that bigger inputs mean bigger outputs. So if we're on a graph and we go bigger inputs, okay, and we're getting bigger outputs, here's that critical point. That is part of the increasing part of the function. But now I'm going to go to my decreasing part of the function, right? And as my x's go this way, this same value at the maximum is still following the definition of a decreasing function. So that maximum up there is included in both the increasing and the decreasing. So our critical points are included in both increasing and decreasing, okay? Now, how do we determine where a function is increasing or decreasing? First thing you do is you find the zeros of f prime of x and you put them on a number line, okay? Remember, we've done all these kinds of number lines before. And we sample points in to find when it's positive, negative, positive, right? And if the derivative, we're going to label it. If the derivative is positive, then our function is increasing. If the derivative is negative, our function is decreasing. If the derivative is positive, our function is increasing. Then we make our conclusion. Were we supposed to state when it was increasing or when it was decreasing? What were we finding? And justify your answer by making a statement connecting the intervals to the sign of the derivative. So you have to say f of x is increasing on this interval because f prime of x is greater than or equal to 0 if you're doing increasing, or f prime of x is less than or equal to 0 if you're doing decreasing. We're going to look at the first derivative test and relative extrema. So, for the first derivative test, if a critical point of f of x is a relative minimum, only if f prime of x changes from negative to positive, because if the derivative is negative, the function's decreasing, and then when the derivative is positive, the function's increasing, which means that turning point, which is our critical point, is a minimum, okay? Now, a critical point is a relative maximum if f prime of x changes from positive to negative. So when the derivative is positive, the slopes of the function are positive, so it's increasing. And then when the derivative is negative, the slopes are negative, so the function is decreasing, which means this turning point up here is a maximum at that critical point, okay? So the first derivative test, when you need to justify this, we need to make a number line. Make sure this is labeled. You must label your work, okay? I am labeling the top as the derivative, so I am saying that the derivative is negative and then the derivative is positive. On the bottom, I'm talking about f of x, so that if my derivative is negative, my function is decreasing. If my derivative is positive, my function is increasing. Now notice, if we decrease and then increase, it makes sense that our graph looks like this, and we have a minimum. So what we would write on a test is, f has a relative minimum when f prime of x changes from negative to positive. Okay, let's take a look at the other example here. So again, my top is labeled f prime of x. I show that the derivative is positive and then it's negative. Well, the bottom is going to be for my function. If my derivative is positive, my function's increasing. When my derivative is negative, my function is decreasing. And it makes sense that if we increase and then decrease, that we have a relative maximum. So we would write f has a relative max when f prime of x changes from positive to negative. Okay, so far so good? So here's a graph example, okay? So here's a graph, and I'm going to put a number line right underneath it, like this, okay? Let's put f prime of x on the top, f of x on the bottom, and we've got A, we've got B, and we've got C. Now this is the graph of f of x, okay? So that's this part of the graph. Now this graph is decreasing, right? At the beginning, we can see that it's decreasing. And notice all these slopes are negative, aren't they? All the way down here to A. They're negative. So we have negative slopes until we get to A. Then, between A and B, my graph is increasing. And you'll notice we have positive slope, positive, 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 positive slopes, right? Positive slopes, and my function was increasing. Then you'll notice that our function is decreasing again. Decreasing, 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 where we have negative slopes, which means our derivative is negative. Then we're looking as when the x's are greater than c, our graph is increasing again, right? And if we look at this graph, we've got positive slopes going up, going up, going up, going up, going up, going up, going up. Positive slopes means a positive derivative. So there's several things that we can say here. We can say that this graph, f of x, is increasing for a less than equal x less than equal b, and the x is greater than or equal to c since f prime of x is greater than or equal to 0. We can also say that f of x is decreasing for the x is less than or equal to a and b less than equal x less than equal c since f prime of x is less than or equal to 0. So these two statements are how the justifications will look in a problem. So let's try a problem. If f of x is 1/3 x cubed plus x squared minus 48x plus 5, for which x values does f of x have a relative maximum, and justify your answer? Okay, so the first thing is I'm going to rewrite f of x so I can see it better. 1/3 x cubed plus x squared minus 48x plus 5. Now I'm going to find my derivative so that I can find my critical points. 1/3 x cubed, the derivative of that is x squared, plus the derivative of x squared is 2x, minus the derivative of 48x is 48, and the derivative of 5 is 0. We want to know when this derivative is 0, so we have x squared plus 2x minus 48 equals 0, and we need to factor this. If we factor, what multiplies to negative 48 adds to 2, that's a positive 8 and a negative 6. So I have critical points at negative 8 and at 6. So I'm going to set up my number line and watch how much we can learn about this function. We're going to put our critical points, negative 8 and 6. We're going to label the top for the derivative and the bottom for the function. Okay? Now, if we pick a number smaller than negative 8, if I pick a number smaller than negative 8, say negative 10, and now I'm going to plug it into this factored form. Negative 10 plus 8 is a negative number. Negative 10 minus 6 is a negative number, and negative times negative is a positive. Now, if I pick a number between negative 8 and 6, like 0, and I plug it into that same factored form, 0 plus 8 is positive, 0 minus 6 is negative, and if I multiply them, that's a negative number. Then we're going to pick a number bigger than 6, any number you want, take 100, and we'll plug it in here. 100 plus 8 is positive, 100 minus 6 is positive, so their product is positive. Now, if my derivative is positive, that means my function is increasing. If my derivative is negative, my function is decreasing. If my derivative is positive, my function is increasing. So look at this. This even gives us an idea. We're increasing, decreasing, increasing. We even have an idea of the shape of the graph. And if you look at negative 8, you can see here we're going to have a maximum, a relative maximum, because my end behavior is going to decrease and increase without bounds on the ends, right? And at 6, we're going to have a relative minimum. So now we need to answer the question. For which x values does f of x have a relative maximum? That's this one, right? So we're going to say f of x has a relative max at x equals -8 since f prime of -8 is 0, that tells us it's a critical point, and f prime of x changes from positive to negative. Okay, so yes, you need this if somewhere else you have not said that -8 is a critical point because the derivative is 0. It has to be identified as a critical point before you can use the rule that f prime of x changes from positive to negative gives you a maximum. Some notes about justifying. Sign charts or the number lines are used so you can stay organized, okay, and keep track of a function's behavior around the critical points. Sign charts do not count as justification. They do not count as a full justification. Make sure you include a conclusion sentence, full sentences. And by the way, no pronouns. Do not tell me it is increasing because it is positive. No pronouns. Justifications about extrema must include information about the derivative. If you don't talk about the derivative, you are not justifying. You cannot tell me because the function changed from increasing to decreasing. No, you have to talk about the derivative. All right, guys, that's it for today. I'll see you soon. Have a good one.